next part of the problem, right? Come to the question. For this question, we already find out this. I0 plus was 2 ampere and V0 plus was 4 volt, right? Now in the next step, we have to find out d by dt of I0 plus and d by dt of V0 plus. And in the third step, I infinity and V infinity, okay? So, friends, at t equal to 0, we are studying this circuit, okay? At t equal to 0, we just open the switch. Is it okay? So, we are opening the switch at t equal to 0. So, what is the condition of the circuit after opening the switch? The condition is like, I think you people will agree with me, the 4 will as it is. This is 12 volt. This inductor I can replace with the current in it. Initially, the current was 2 ampere, right? So, at t equal to 0 plus also, the current in the inductor is 2 ampere. That's why I'm replacing the inductor by this. Okay. Now, come to this portion. This is 2 ohm. Now, what about this? You have opened the switch. Okay. I opened the switch. Come here. Here, I can replace the capacitor with the voltage whatever we got over here. Because at 0 plus also the voltage should be 4 volt across the capacitor. So at t equal to 0 we are drawing the circuit. So the voltage across the capacitor will be 4 volt. Like this it is. Okay. So now our task is to find out d by dt I0 plus. Where is the I? Here is the I. Where is the V? Here is the V. Okay. This is I. Now, if you remember the relation between capacitor voltage and inductor current, if you remember, let me come over there. If you remember this formula, so the IL is nothing but V, voltage across inductor is nothing but L di by dt. Is it correct? L di by dt. Okay. This is the relation between voltage and current in the inductor. Similarly, for capacitor, the relation is IC equal to C dVc by dt. Is it correct? This is the relation between current and voltage for the capacitor. This is the relation between current and voltage for the inductor. Okay. Now friends, if you will see this carefully, they are asking for di0 plus by dt. Though this is the function of t, like this it is. This is the function of t. Now my task is to find di0 plus by dt, like this. So what is the value of this? This L will go this side, this is also 0 plus. So VL is the voltage across inductor. Is it okay? VL is the voltage across inductor. So if you are able to find out this voltage, this voltage value across the inductor, you will divide that with the L and you will get d by dt of I0 plus. Is it okay? Because this is the relation given over here. He is asking for d I0 plus by dt. So d I0 plus by dt is nothing but VL by L. Now the VL is voltage across this. So can I get this branch is open. So this is the meaningless in the circuit. So I have to get the value of VL. So the current in the circuit is 2 ampere. So voltage drop across this 4 will be 8 volt, right? Now I will apply. So this is 8 volt. This voltage across the inductor is VL, suppose. Here is the 4 volt. So I can apply the KVL over here in this entire loop. So I'll start with the 12 volt. Okay, fine. I'm getting this is minus 8 volt. Okay. Here I'm getting minus VL. Okay. and here I'm getting minus 4 and again 12, so it's 0. So now you can see this, see 12 minus 8, 4 minus VL minus 4 is nothing but 0, so VL is 0. So VL is 0, right? Once you got the value of VL, that is 0, so can you get the DI, this one value? Yes, you can get now, because he is asking in the question, they're asking for this, right? And this is nothing but VL by L. VL is 0. L is 0.25. So finally this is 0. 0 what? Ampere per second. Ampere per second. So this is all about d I0 plus by dt. Now come to the this one. So for this V, you have to come to the capacitor equation. Capacitor equation is, now what they are asking, they are asking dV0 plus by dt. Yes, we have in this formula dV0 plus by dt. So this is nothing but IC by C. What is the IC? What is the current across the capacitor? It's 2 ampere. So the value of this is nothing but 2 ampere divided by 0.1. So this is nothing but 20. 20 what? Volt per second. Volt per second. This is all about this equation, right? This one. Now come to the next. They're asking, find out I infinity and V infinity. So if you remember, in the starting I told you, this is the time at 0. This is minus infinity. This is a steady state. Okay, before t equal to 0. And after a long time, again we are having steady state. So if the circuit is working from a long time, so we can say that it is in steady state now. So before we open the switch or close the switch, see, before t equal to 0, the position of the switch was closed. So this is steady state here. But they're asking I infinity, V infinity, means after t equal to 0, after a long time, what is the situation for this, right? So I have to find I infinity and V infinity. So earlier we discussed at the infinity, at steady state, the conditions for voltage across the capacitor and current and or I can say the conditions of inductor and capacitor is, see, t equal to infinity means S equal to 0. Am I okay? Now XL is nothing but, if you remember, SL, X is 1 by SC, correct? So if S is 0, XL is 0. 0 means you have to replace it by short circuit. Come to this, 1 by 0 means infinity. You have to replace this by, open circuit, right? For the steady state. How you can get this? That what you have to do, you have to open it or short it. You can easily get it. Here the time value is infinity. So the frequency value is 0. We know these two formulas, so we can get the conditions for inductor and capacitors. So if you draw the new circuit, you will get 4, fine. The inductor you will replace by short circuit, okay. What about this? You are opening at t equal to 0. So there is no meaning for this branch. Open. The circuit is open. Will there any current in the circuit? Tell me. No, because here it's open. So I can say I infinity is open. I infinity, though this circuit is given for the steady state, so I can say I infinity. Is there any current? No, 0 current. Why current is 0? Because circuit is open. Okay. Now come to the V infinity. Right. V infinity, where is the V infinity? Here is the V infinity. There is no drop, so this 12 volt is directly nothing but the V infinity. So V infinity is nothing but 12 volt. Or you can apply the KVL over here. 12 plus minus 4 into current 0. This is minus V infinity equal to 0. So V infinity is nothing but 12 volt. So this is all about this question. Okay, this is very important as per the basic concepts is concerned. Okay, now come to the next one. Now we'll see the first order circuit or the source free RC circuit. Source free. Here the concept is given the source free. Source free means in your circuit there is no independent source, right? When this condition comes in the circuit, see, I'll show you an example over here. Suppose here is the switch given. Capacitor is given over here. Input excitation 12 volt, take it. 2 ohm, 3 ohm, 0.1 farad. Is it okay? At t equal to 0 you are opening it. At t equal to 0 you are opening the circuit. Means before t equal to 0 it was closed. Before t equal to 0 it was closed. Somehow it was like this. So when it was closed, there is a voltage drop across the this resistor and voltage stored in the capacitor. Okay, fine. Now if we will open the circuit, the remaining circuit will be like this. .1 farad. This is the remaining circuit. Correct? So for this circuit, this is the open branch. So this is the meaningless. So our remaining circuit is 3.1. So in this circuit, I am asking, is there any independent source? No. That's why this type of circuit I called source free. Source free circuit. This circuit is source free. There is a no source over here. Okay. Now come over here now. First order circuit, the source free RC circuit. RC circuit means the source free circuit will contain resistor and capacitors only. The situation will be like this, you can see. Means after disconnecting the circuit from the initial circuit, we are having capacitor and resistor remain. Okay. This is the condition. A source free RC circuit occurs when its DC source is suddenly disconnected. The energy already stored in the capacitor is released to the resistor. So in this case, the energy stored in the capacitor when it was connected to the source will be released in the circuit. Okay. So if you will observe this circuit, and here the voltage you are taking, this is the V, the current in the capacitor is IC, the current in the resistor is IR. So at this node, IC plus IR equal to 0. Okay, both are the outgoing currents. So IC plus IR equal to 0. Now, we have this relation C dV by dt. This is the relation C dV by dt. This is the relation between current and voltage for the capacitor. So I replace this IC with this. And what about IR? IR is nothing but V by R. V by R. So this is the first order differential equation. Here the order is 1. That's why we are saying is the first order circuit. So we can solve this. I think you people know differential equation, how to solve it. So here, if you will solve it, you will get Vt equal to V naught e to the power minus T by RC. T by RC, where RC is nothing but time constant tau. Okay. So this is the very important equation. Vt is nothing but V naught e to the power minus T by RC. This is the exponential decay you can see. Means if initially you have the value of voltage is V naught, now as the time will increase, this will decrease. Exponentially decrement is there. Means at t equal to infinity, at a steady state. Means after a long time, see, this capacitor is disconnected from the source. So whatever energy stored by the capacitor will be delivered in the circuit now. So will it be continue till infinity? No, after some time it will be 0. The entire energy stored by the capacitor will released and the energy will be dissipated through the R. So after some time this circuit will become dead circuit. Is it okay? So at t equal to infinity, if you will put over here, so e to the power minus infinity is 0, v2 equal to 0. At a steady state, whatever the voltage in source free circuit is there is nothing but the 0. After some time, there is a no 0. The stored energy is dissipated through R. So this is all about the first order circuit having RC. Okay. So this is the exponential decay. Here, the definition of time constant is coming. The time constant of a circuit is the time required for the response to decay to a factor of 1 by E, or 36% of its initial value. What it's saying, see, if the initial value of the voltage is this, after some time, it's taking time and it's coming to 36.8% of the initial value. So the time taken to come to this value is nothing but tau, time constant of the circuit. This shows the voltage response of the RC circuit is an exponentially decay of the initial voltage. Since the response is due to the initial energy stored and the physical characteristics of the circuit and not due to some external voltage or current source, it is called the natural response of the circuit. The voltage decreases is expressed in terms of time constant denoted by T. I hope this is pretty clear to you people. Now come to this very beautiful problem. Let Vc is given. Initial condition across capacitor is given. Vc is given 15 volt, 0, right? Find Vc, Vx and Ix as t greater than 0. He is saying find out these things at t greater than 0, right? So how to solve this circuit? See friends, so this is nothing but the application of whatever we have seen, the source free circuit, source free RC circuit. See here only RC circuit is given. So for the source free RC circuit, the Vc, they are asking for the Vc, right? So we already seen that Vc, Vct I can say, Vct is nothing but V0 e to the power minus t by tau volt, right? Where tau is nothing but RC, correct? So how to calculate RC? Tau is calculated with respect to the capacitor always. Means across these 2 points A and B, calculate the resistor of the circuit, equivalent resistor. Then multiply the resistance with capacitor value, so you will get the time constant of the circuit, right? So across A and B, forget all about this data. Across A and B, what is the value of equivalent resistance? If this is open, across this A and B, 8 and 12, they are connected in series, and the 20, the combination of these two is 20 ohm, this 20 ohm connected with parallel with this. So 5 into 20 divided by 5 plus 20. This is nothing but the resultant, right? 5 into 20 divided by 25, 5, 5, 5 4s are. So this is 4 ohm. So tau is nothing but 4 into 0.1. So this is 0.4. Tau is 0.4. So your equation is Vct V0 e to the power minus t by 0.4. 0.4 is nothing but 1 by 0.4 is nothing but e to the power minus 2.5 t. V0 is given over here. Yes, it's given over here. So V0 is nothing but 15 e to the power minus 2.5 t. So this is your Vct. Now you have calculated the Vct, the voltage across capacitor at t equal to 0. Now your task is to calculate Vx and Ix also. So first I'll remove this. Now here you calculated the voltage, and that is 15 e to the power minus 2.5 t. Okay, you have to calculate the Vx. So here the voltage is 15 e to the power minus 2.5 t. So can you divide this? Can you find out Vx? Vx is nothing but this 12 into this 15 e to the power minus 2.5 t divided by summation. Summation is 20. This is nothing but Vx. Simply I'm applying the voltage division rule over here, right? So this will be like 3 by 5 into 15 into e to the power minus 2.5 t. Okay. So 5 3s are 5 3s are 15 and 339 e to the power minus 2.5t. Am I right? Okay, yes. This is 3 and 3 3s are 9 e2. This is nothing but the Vx. So he is asking for the Vx at t greater than 0. Yes, this is the value of Vx. Now he is asking for the Ix also. So Ix, you have the Ix by Ohm's law. Vx divided by 12. So Vx is 9 e to the power minus 2.5t divided by 12. This is nothing but 3 by 4 e to the power minus 2.5t. This is nothing but Ix, ampere. And this is in volt. Okay, this is all about this question. Come to the next. So this is the next question, and this one I'm leaving for you, okay? But he is saying the switch in the figure has been in position A for a long time. In the position A for the long time, at t equal to 0, the switch moves from position A to B. At t equal to 0, the switch is coming to B. The switch is a make before break type. The switch is a make before break type. So there is no interruption in the inductor current. Means it is saying that it's immediately coming to this. At t equal to 0, immediately the switch is coming to B. Okay. Now what they are asking? They are asking IT for t less than 0. Where is the IT? Here is the IT. At t less than 0. He is asking for IT. Then V just after the switch has been moved to position B. Where is the V? Here is the V. He is asking V just after the switch has been moved to position B. And in the next one, the VT long after the switch in the position B. So this is, I'm leaving for you. I think you can do it very easily. Come to the next one, and the next part of the unit is the source free RL circuit. Earlier we have seen the RC. Now we'll see the RL. In the RL circuit, the situation will be same. The circuit will be connected with the source, but suddenly it will be disconnected. So whatever energy stored in the storing element will be delivered to the resistance. So here also see inductor over here. This is the resistor over here, and current in the circuit is I. Okay. So our goal is to determine the circuit response, which will assume to be the current IT through the inductor. Okay. In the RC circuit, we have voltage VC over here. Because for the capacitor, we calculate the voltage, and for inductor, we calculate the current. Okay. So current here, can I apply the KVL over here? If you will apply KVL over here, you will see VL plus VR equal to 0. In that case, we were having IC plus IR equal to 0. In this case, we are having VL plus VR equal to 0. Now, do you have the relation between voltage and current for the inductor? Yes, you have. This is nothing but L di by dt. And VR is nothing but Ri. So, if you will solve this differential equation, you will get IT is nothing but I naught e to the power minus RT by L. Is it okay? Where tau is nothing but L by R. So, for the capacitor, the voltage value was V naught e to the power minus T by tau, where tau is nothing but RC in the case of capacitor. Here you will calculate current IT, and current IT is nothing but I naught e to the power minus IT by tau. And here tau is nothing but L by R. Is it okay? So this is the current equation. Here also the current is decaying exponentially. See, you can see here. And the value of current decreasing to 36.8%, and the time taken is nothing but the time constant. Okay. So these are the two equations in source free circuit. For the capacitor, Vt is nothing but V naught e to the power minus T by tau. And for the inductor, the current is It equal to I naught into e to the power minus T by tau ampere. This is volt. Is it okay? So we'll see one example based on this. Assume I naught is 10 given. Where is the I naught? here this one is given. Calculate IT and IXT in the circuit. This is similar to that whatever we have seen earlier based on the capacitor concept, right? So we need tau. Tau is nothing but L by R. L is given over here, and across L I have to find the resistance of the circuit. Though the circuit contains the dependent source, so the calculation will be like this. So for this circuit we can't directly find out the tau because we need the equivalent resistance. To find out the equivalent resistance, we are fetching this dependent source in the circuit, and we need independent source. So one another way to solve this circuit is like by doing this question, mesh analysis I can apply over here. Assume this current is, suppose this current is I1, and assume this current I2. Okay, this current is I1 and this current is I2 over here. So if I'll apply the KVL over here, so the voltage drop across this will be like this, and the VL equal to L di by dt. This is the relation between current and voltage for the inductor. So we need the voltage over here. So voltage is given as 1 by 2 di1 by dt. Correct? This is I1. So this is all about I1. Okay. So okay, fine. Now come over here. I1 is coming from this side, I2 is coming from this side. So it will be okay, let me take it out first. The given circuit is like okay. The current given over here is Ix. The current in this given is I, and the value of this inductor is 0.5. So the relation between the voltage and current for the inductor is L di by dt. So the voltage across inductor is means the voltage over here at this point is L. L is nothing but 1 by 2 given di by dt. Is it correct? The value of this is 4. So I'm going to do this circuit by KCL directly. Why? Because I'm having two nodes. One is grounded, one non-reference node. Only one equation I'll get. So easily I can solve that equation. Okay. So here at node A, I am applying the KCL or nodal analysis, right? So the current, outgoing current is plus I given over here. And what about this branch? This branch is 1 by 2 di by dt, voltage divided by 2. So this becomes 4 plus, come to this branch, 1 by 2 di by dt minus 3I divided by 4 equal to 0. Okay. So we'll resolve this now. I plus di by dt 1 by 4 plus 1 by 8 di by dt minus 3 by 4 I equal to 0. Okay. Take 8 LCM. This will be 8I plus this will be 2 di by dt plus di by dt minus 6I equal to 0. Okay. So 8 and this 6, it will be 2I plus here it's 2 and 1, 3 di by dt equal to 0. Is it okay? So your equation is like, differential equation is di by dt plus 2 by 3I equal to 0. This is your differential equation. Now can you solve this differential equation simply? The result will be I naught e to the power minus 2 by 3 dt. 2 by 3t. Okay. So your I naught is 15. So this is nothing but 2 by 3t. Okay. So finally you have the current is nothing but e to the power minus 2 by 3t ampere. This is the current. They ask for current IT. So you have found the IT. Now they are asking for the IX. Here IX. So yes, you can find out the IX also. So this is up to you. Okay. Now come to this question. The switch in the circuit, the figure, has been closed for a long time. The switch is closed for a long time. And at t equal to 0, the switch is opened. Calculate IT for t greater than 0. This current we have to calculate for t greater than 0. This also homework. Okay, come to the next. The singularity functions. Singularity functions are the functions that either are discontinuous or have discontinuous derivatives, right? Singularity functions, also called the switching functions, are very useful in circuit analysis. They serve as good approximations to the switching signals that arise in circuits with switching operations. Okay. The unit step. I think you people know about this unit step. The unit step function ut is 0 for negative values and values of t and 1 for the positive values. So this is the graph for the unit step. Singularity function unit step is nothing but for all t less than 0, the value of the function is 0. For all value t greater than 0, the value of the function is 1. So the value of function is 1 for all t greater than 0 and 0 for all t less than 0. So this is nothing but the unit step function. I think you people studied this in the signal and system also. Okay. So here we are briefly discussing about this function. So the unit impulse function, now come to the unit impulse function del t, is 0 everywhere except at t equal to 0. At t equal to 0, the magnitude is given as infinity, but when we calculate the area, it will be 1. Minus 0 to 0, del t dt is nothing but 1. So for direct unit impulse functions, the magnitude at t equal to 0 is infinity, but the area is 1. Okay. So the impulse function is nothing but the derivative of unit step function. Derivative of the unit step function. For t less than 0, the value is 0. For t greater than 0, the value is 0. For exact t equal to 0, it's undefined because it's infinity. Now, impulsive currents and voltage occur in the electric circuits as a result of switching operations or impulse sources. Although the unit impulse function is not physically realizable, just like ideal source, ideal resistors, it is very useful mathematical tool. Okay. So this is nothing. Impulse response means the value of the function at a particular point only. Okay. At t equal greater than 0, it's 0. T less than 0, it's 0. It is given for only exact point t equal to 0. And the magnitude of that function is infinity. The area is 1. Now integration. See, if you will integrate the unit step function, you will get the ramp function. Integrating the unit step function results in the unit ramp function. This is nothing but the ramp function. This is nothing but the ramp function. Means for the t greater than 0, greater than equal to 0, the value is given by t direct. This is the line. Okay. But for t less than 0 and at 0, the value of the function is 0. This is nothing but the unit ramp function. The unit ramp function is 0 for all negative values of t and has a unit slope for positive values of t, see this is the slope over here, maintained everywhere, right? So we have seen unit step, impulse. Now we have seen the ramp function. Now come to the next. So friends, now we are coming to the very important concept, and that is the complete response. See, suppose you are taking circuit. You are taking circuit in which you are providing input and getting output. So this output in the transient family given by two things. Number one is transient response and second is steady state response. See, in this figure, you applied some input, you are getting some output. So up to here, this is the transient part. But after this part is steady state. This is the steady state part. Okay. This is nothing but the output of someone. So output contained are comprised by two things. One is transient part, one is the steady state part. So when you will add up these two things, so you will get the complete response. You will get complete response. Okay. So can I say the complete response is nothing but the transient response, means the temporary part. Why temporary? Because after a certain time it will be vanished. And steady state is the permanent part. Permanent part means steady state response is the response for which the system is designed. Okay. So the transient response in the circuits, temporary response, that will die out with the time. So at t equal to, after some time it will be gone. Okay. The steady state response is the behavior of the circuit a long time after an external excitation is applied. Steady state, I told you, when the circuit is kept for a long time working, so I can say the circuit is in steady state. Now the complete response formula is given over here. Complete response xt is given as x infinity plus x0 minus x infinity e to the power minus t by tau. This is given the complete response of the circuit. Here this is the steady state response, and this part is, see, the exponential part means transient part. So this is the transient part, and the constant part is the steady state. Okay. So once we know the x0 and x infinity and t, almost all the circuit problems in this chapter can be solved using the formula. Okay. Very important formula I am going to provide you. Very important. Voltage equation for the capacitor, where V0 is the initial voltage at t equal to 0 plus, V infinity is the final or steady state value. Thus, to find the step response on RC circuit require three things: the initial voltage, the final voltage, and time constant. If you are having these three things for a particular circuit, you can get easily the value of voltage for t greater than 0. What I am saying is, if you have the RC circuit, whatever the circuit is, but it contains R and C. Okay. Now the question is, find out the voltage Vt across the capacitor for t greater than 0. Means t greater than 0 means you have to find out the Vt. They are not asking V0 minus or V0 plus. They are not asking this. They are asking, find out the general solution. So for the general, we are giving Vt directly. So formula for Vt across the capacitor is nothing but V infinity steady state plus V0 minus V infinity e to the power minus t by tau, where tau is the time constant. So if you have V infinity across the capacitor, means steady state value of the capacitor. If you have initial value of the capacitor, and if you have time constant of the circuit, you can easily find out the Vt without calculating further in the circuit. Directly put this formula if you are having these three things. If you have V infinity, V0 and tau, put in this equation and get the Vt directly. So this question sometime asked in the GATE exam. This is the very important concept. Okay. So based on this concept, we'll solve this. The switch in the figure 4.43, here is the switch, has been in position A for the long time. Initially the switch is like this. So for a long time it is at A, and at t equal to 0 the switch moves to B. Determine Vt for t greater than 0. Where is the Vt? Here is the Vt. For t greater than 0 they are saying. And calculate its value at t equal to 1 second and 4 seconds. It's very easy problem. If you know the formula, the Vt is nothing but V infinity plus V0 minus V infinity e to the power minus t by tau. If this formula you know, this question is very easy for you. If you don't know, so it will take time for you. Okay? It will take time. So Vt, I need V infinity. Okay, fine. I need V0 and I need tau. So initially the switch is connected with A like this. The circuit is in steady state. Initial steady state means at minus infinity I'm talking about, because at t equal to 0 I'm changing the switch, and at this stage after a long time it will be t equal to infinity. So in the steady state the capacitor behaves like an open circuit. So your circuit will be, let me erase it first, your circuit will be 3K 24 5 connected over here, and this is open for a long time means minus infinity, t is infinity, s is 0. If s is 0, xc is nothing but infinity, open circuit. So I'm writing it open circuit. So can you calculate over here 0 minus? This is the V0 minus, right? Though the circuit is in initial steady state, but after some time at t equal to 0, you are changing it. Means before t equal to 0, the value will be V0 minus remain. Is it okay? So the value of this voltage over here, this is the open circuit. So directly no current is going to this branch. 3 and this 5K, they are connected in series. Okay, because this is not a point, this is the open, useless. Okay, so voltage across 5K is nothing but the V0 minus. So voltage division rule, 5K into 24 divide 5 3 8K, KK will get cancelled, and 8 24 8 3, and this is 15. So 15 is the voltage over here. So you calculated VC0 minus is nothing but 15. Similarly, V0 plus will be 15 volt. You need V0 plus to solve that particular equation, whatever we have seen. So you calculated the 15. Okay. Your formula is Vt, V infinity plus V0 minus V infinity and minus t by tau. Now you calculated V0, okay? You need to calculate V infinity. V infinity means after t equal to 0. So at t equal to 0 you are connected it. After a long time, after a very long time, the circuit will be, or the capacitor will be open again, because you need to calculate V infinity now. So now the circuit will be again, this is 4, this is 30, and this is open circuit. T equal to infinity I am talking about. Again this is the open circuit. So V infinity is nothing but 30 directly. You calculated this one also. V infinity is 30. V0 is 15. Now you need to calculate tau. So tau is always calculate. See, if you are calculate the tau, consider the output stage. Means at t equal to infinity, whatever given in the circuit. We will not consider to get this tau We'll not connect the switch to A. We'll connect switch to the B, because this is the last condition we are talking about. So here across capacitor, you have to find the R equivalent of the circuit. R equivalent circuit, the battery will be short circuited. This is the 4K. And capacitor is 0.5. So tau is RC. R is 4K. C is 0.5 milli. We will cancel, and this is the 2. 2 seconds is the time constant. Now 2 seconds is the time constant. Everything is available now. Whatever they are asking, we can reply now very easily. Vt is nothing but V infinity means 30 plus 15 minus 30 e to the power minus t by 2 volt. So this is nothing but 30 minus 15 e to the power minus t by 2 volt. This is my answer. So friends, I'm saying you, if you remember this formula, again and again I'm writing this, Vt is nothing but V infinity plus V0 minus V infinity. If you remember this formula, this is the formula for the voltage across capacitor. And if you have these three values, you can easily calculate the Vt. Okay? So this is all about. Now come to this one. The switch in the figure is closed at t equal to 0. At t equal to 0 it's closing. Before that it was opened, right? Find it. Where is the it? Here is the it. And Vt for all time. Not that u minus t equal to 1 for t less than 0. Where is the u minus t? Here is the u minus t. But he's saying u minus t is 1 for all less than c. We have seen ut is nothing but this is ut, right? This is the graph for the ut. Now u minus t, we are changing the time, it will become like just opposite of it. It's mirror of it, right? So for t less than 0 it will be 1. That's why he mentioned there also. U minus t equal to 1 for t less than 0. Okay? And 0 for t greater than 0. Also v minus t. Okay, this is the relation between ut and u minus t. What he is asking that find out it and vt for all time. It and vt for all time. Okay, so can we find out? Yes, we can find out it. So they are saying the switch is closed at t equal to 0. Before that it was open. Okay, fine. Wait a minute. It was open, so the circuit was like 5. Before t equal to 0 we are talking about. Before t equal to 0, the value of u minus t is 1. So I can write it 20. I can write it 20. What about capacitor? Capacitor will be open. Capacitor will be open because before t equal to 0, we are having the circuit working in a steady state, initial steady state for a long time. Okay, so I can calculate the V now. The V is 20 volt directly, right? Here the switch is open like this condition, right? So this V0 minus is nothing but 20 volt directly. And this will be nothing but the value of 0 plus also. Now he is asking that for all time, means find out at t. Okay. So you can find out this Vt across the capacitor. The formula is same. Vt is nothing but V infinity plus V0 minus V infinity e to the power minus t by tau. Okay, so this one is completed. Now you have to find the V infinity. V infinity means switch off the circuit. Oh, sorry. Close the switch. Please remember this 20. Okay, I'm erasing all these things. Now the next one is we are connecting the switch. Now your circuit is this is 5. After a long time it will be open. 3 ampere like this. What about this battery? For t greater than 0, it's 0. So this is 0. 0 means short circuited. The voltage is 0 means short circuited. It is 5. This one is open circuit and this is V infinity. For a long time I'm saying that the circuit is kept for a long time, so it will be automatically in a steady state V infinity. We are having only 3 conditions. One is 0, minus infinity, infinity. At t equal to 0, you are changing the switch condition. So before changing, the circuit was kept for a long time. So I can say initial steady state. At t equal to 0, initial state, we are changing the switch. So we are getting two things, 0 minus, 0 plus. After a long time, I am having steady state condition. Okay. Come to this circuit. I have to calculate V infinity. You are having 3 ampere current over here and 2 parallel branches. So if you can find out the current in this, that current and into 10 is nothing but the V infinity, right? So I'll divide this current. The current in this is 5 into 3 divided by 15. 5 3s are, and this is 1. The current over here is 1 ampere. So V infinity is nothing but 10 volt. V infinity is 10 volt. Okay. Fine. Now, you had calculated V0. That was 20. You have calculated V infinity 10. Now you need tau. Tau you have to calculate. So, come to the steady state condition. Open the capacitor and find out the equivalent resistance across A and B. So this is your circuit at a steady state. Everything is open. Capacitor is open. This is short circuited. So here A and B. This is the current source. You can open it. We'll open it because I'm calculating the R equivalent. R equivalent current will be open and the voltage will be short circuited. So this 5 and this 10, they are connected in parallel. Okay. So parallel branch equivalent 5 into 10 divided by 15. 5 3s are 10 divided by 3. This is nothing but your R. What is time constant? Time constant in R into C. R 10 by 3. What is C? C is 0.2. 0.2. This is nothing but 2 by 3. 2 by 3 is the tau. Now, can you calculate Vt? Yes? Wait. Now, Vt is again V infinity plus V0 minus V infinity e to the power minus t by tau. V infinity you calculated 10. This was 20 minus 10 e to the power minus 2 by 3 t. Okay. What was your tau? Let me check. Your tau was R into C. The equivalent R you calculated was 3 by 3 into 0.2. It was 2 by 3. So this will be 3 by 2. 3 by 2. Okay. So the Vt final is 10 plus 10 e to the power minus 3 by 2 t volt. I hope this is clear to you. Now you can understand what is the importance of this formula. Okay. Now the next one he is asking for the IT. Where is the IT? Here is the IT. You calculated Vt over here. So can you calculate this IT? Can you calculate this IT? Yes, you can calculate. IT is this 20 U minus T, or 20, I'll say 20 minus this entire thing, A divided by 5. This is for t less than 0, and for t greater than 0 this will become 0. So 0 minus Vt divided by 5. This is for t greater than 0. I hope this question is clear to you. Come to the general equation for the inductor now. For the inductor, the general equation IT is I infinity I0 minus I infinity e to the power minus t by tau. Okay, when you will compare with voltage equation in capacitor, so their Vt is V infinity plus V0 minus V infinity e to the power minus t by tau. Is it okay? So you can compare these two things. For the inductor, the current is IT equal to I infinity plus I0 minus I infinity, where I0 and I infinity are the initial and the final values of the current I. To find the step response of the RL circuits, we require three things. Again, three things. We need initial current, I0, we need final current, I infinity, we need time constant. If you have these three things in your hand, you can easily find out the IT. Okay. Come to this question. Find IT in the circuit for t greater than 0. Assume that the switch has been closed for a long time. At t equal to 0, you are closing the switch. Wait a minute. So for this question, the circuit is given over here. Okay. Find out the IT in the circuit for t greater than 0. Assume that the switch has been closed for a long time. Where is the switch? Here is the switch. And this is the current. We have to calculate IT. Okay. So here they are giving the condition at t equal to 0, it's opening. Right. Before t equal to 0, it was closed. So when it was closed, can I calculate I is 0 minus? Yes, it was closed. So if this is short circuited, so this is the meaningless in the circuit. This 3 ohm is the meaningless in the circuit. So for initial steady state, the inductor behaves like a short circuit like this. So your current I0 minus is 10 divided by 2, 5 ampere. 5 ampere. Similarly, if you are having I0 minus, you are having I0 plus, and that is 5 ampere. Okay. Now you have to calculate I infinity. You have to calculate I infinity over here. So I infinity 5 ampere. Okay. Please remember that. I infinity. Now you are opening this. You open this. Again the steady state. This will behave like a short circuit. Okay. And your circuit is like this. So I infinity is nothing but 10 divided by 5. This is short circuited. So this is 2 ampere. Is it okay? Now 2 ampere is okay. I infinity is okay. I0 was 5. I infinity is 2. You need tau also. Tau at the steady state. Always calculate at the steady state. So across this point A and B, you can calculate first the equivalent resistance. The equivalent resistance is, this is the short circuited. 2 and 3 they are connected in series. So 5. So this is the 5. Tau is nothing but L by R, if you remember this. So L is 1 by 3. 1 by 3. R is 5. This is 5. So, sorry, this is 5. So this is 15. I hope this is clear to you. Now, come to the formula. The formula is, IT is nothing but I infinity plus I0 minus I infinity e to the power minus t by tau. What is I infinity? 2 plus what is I0? I0 is 5 minus 2 e to the power minus t by tau. So this is 15. So your final answer is 2 minus 3 e to the power minus 15 t ampere. This is your current. This is your current. So I hope these two formulas are pretty clear to you. Again, I'm telling you, this is the very important formula, and maybe you are getting problem in 2018 GATE from these two formulas only. Any one of them. Okay friends, so this is all about today's class. We'll meet in the next video lecture and we'll finish this transient analysis and we'll switch to the next unit, that is the AC circuits. Okay, so friends, we'll meet again. Till then, take care and bye.